This video will discuss Rolle's theorem and mean value theorem, which cover section 3.2. These are very important theorems, especially in the proof work that goes on in calculus, but for our purposes, this will be a little similar to intermediate value theorem, just trying to give us a little exposure to theorems and the ideas between making sure the assumptions are true before we can reach the conclusion that the theorem gives us, and then a couple of problems also try and get us to find what the conclusion gives us. So let's start off with what these theorems are. The first idea will be Rolle's theorem. Rolle's theorem says, if our function f of x is continuous on a closed interval a to b, that f of x is differentiable on an open interval a to b, and we know that f of a equals f of b. All of these are the assumptions. We have three assumptions that need to be satisfied in order to make this conclusion. The first, that our function is continuous on this interval, then second, differentiable on the interval, and third, that f of a equals f of b. So if all these three things are true, then we can reach this conclusion. And this conclusion is, there exists a c value. This will be an x-coordinate, and that x-coordinate will be somewhere located between the a and b that have been given in the earlier parts. And what's so special about that c value? That c value has a derivative value equal to 0. So before we finally start to see a little more understanding of what this is saying and how this works, let's immediately move into mean value theorem, because they are very, very similar in their presentation. Mean value theorem, or MVT for short, mean value theorem. Mean value theorem starts in a similar way. If my function f of x is continuous on a closed interval, but now this only has a second condition, not a third, and the second condition is the same, and f of x is differentiable on the open interval a to b. We're not going to get the third condition, f of a equals f of b, so we're going to get a similar but slightly different conclusion than we had for Rolle's. We'll still get the then, the backwards e stands for there exists. We'll still get this value c, which will still be an x value. It'll still be an element of the open interval a to b, meaning that c is just some x-coordinate that's located in between these two x-coordinates. But the final conclusion, the derivative at c, it no longer equals 0 like we had here. It equals f of b minus f of a all over b minus a. So what are these two theorems trying to say? And if we really start to understand this, we'll also realize that if we read this carefully, this extra condition in Rolle's theorem is what strengthens this final statement. That this extra condition almost just makes this a special case of what we're presenting in mean value theorem. So what are these two theorems actually trying to tell us? Let's take a look at Rolle's theorem quickly first. If we draw a graph of a function that satisfies these three conditions, well, so I'll just label my graph f of x. I'm going to set up some interval a to b. Let me just put them over here for convenience. So it doesn't matter that they're both positive x values here. That's not going to make any bit of difference. And if I'm going to satisfy the conditions in Rolle's theorem, well, again, three things. Wherever my graph starts when x equals a, it needs to be continuous all through b. So whatever this graph does, the idea of continuous, my graph needs to be connected. So I'll keep this one fairly simple. Let's our function just do this. My graph is entirely connected, so continuous. There's a little bit about why this is a closed interval, just to make sure that everything up to and including this point, no breaks, no holes, and that these are filled in values. The second part about being, differentiable, Now this has the open interval, so everything in between this has to be differentiable. That means the derivative has to exist there. There has to be a tangent line we can draw so that we can measure its slope, and that basically means we can't have any discontinuities, which we've already seen we are covered, and we can't have any sharp points. And this graph I drew had no sharp points. The third condition with that f of a equals f of b, and you'll notice when I drew these, whatever this y value is, that f of a is this y, f of b is the same y value. So this little graph I drew satisfies everything that we have in Rolle's theorem. So what is this final conclusion? There is an x value whose derivative equals 0. A derivative equaling 0, again, the idea of the slope of the tangent line equals 0 means my tangent line is horizontal. Can you look at this picture and just this little region right here, not looking, I don't care what happened before A, I don't care what happens after B, just from A to B, can we see a spot on this graph where the tangent line would be horizontal? I hope we're all looking right here. I'll just change color just so we can try and keep this separate. That spot right there, that would have a horizontal tangent line. So this would be the C value guaranteed by Rolle's theorem. So again, it's pretty nice. This definitely helps. The reality of calculus, Rolle's theorem and mean value theorem are both very important for different proofs. We're not going to do any proofs. We just want to have a little understanding. And again, really starting to understand the only reason we are guaranteed to have this C is because the 3 previous conditions were met. That if I had 2 out of the 3 conditions, that would be continuous, those would have the same y value, but not differentiable, and therefore we're not guaranteed. We might get lucky and have a horizontal tangent line, but we don't have the guarantee that we had here. A couple of more complicated situations, if my graph did something like this, that would also satisfy all 3 conditions now, but now we notice there's 2 possibilities for C. C could be here, C could also be here, right? Both of these would have horizontal tangent lines, so they both could be C. But again, there's no problem with that here. It's just guaranteeing there's at least one C, there might be multiples. So that's Rolle's theorem. What's the difference? What does mean value theorem do? Well, you remove that third condition, now we're not guaranteed that these 2 points have the same y. But other than that, we basically have the same setup. So let me do a fresh one, and let me satisfy the first 2 conditions, and let me make sure that the third condition is not met. So if f of a is up here, and f of b is down here, and whatever the graph does, again, smooth and connected to give us the continuity and differentiability that we need. So again, I'll keep it fairly simple. Let me just do something like this. So this graph satisfies the 2 conditions that we have with mean value theorem. But now, what about the conclusion this time? This time, if we look at the conclusion, we're still getting the C value between A and B, but now the derivative is very different than having a derivative equal to 0. So what is this whole big mess over here? If we look carefully, this is a y value, that's a y value, and then these are both x values. We're taking the y value with b minus the y value at a all over b minus a. Let's realize that represents the slope of the secant line. That if I connected these 2 dots with a straight line, the slope of that line, the slope of that red line I just drew would equal the y value here minus the y value here over this x value minus this x value. And as we always say, that is the definition of slope. So all we have to realize now is that this is saying we're going to find a C that has the same slope as this secant line. We're going to find a tangent line somewhere between A and B, And that tangent line is going to have the same slope as this line. Therefore, that tangent line will be parallel to this secant line. Can you roughly see where that C value is? Trying to draw tangent lines, that would be, that would be, that would be, that would be. But which one is parallel to this one? And roughly, that would be about here. That tangent line here has the same slope as that secant line. Therefore, this would be the C value that we're guaranteed from mean value theorem. Now, the last thing, and then we'll just do one quick problem. This is a nice section, but we're going to move through this fairly quickly. 3.1 and 3.3 have much bigger concepts that we need extra practice with and understanding. So we will do a problem, but first, just to make this last realization. If we look at mean value theorem, and if we add the extra condition that we had in Rolle's theorem, if f of a equals f of b, well then when you look at the slope here, f of b and f of a are the same value, so when you subtract them, you'll get 0. In most situations, that would then make Rolle's theorem a corollary, a quick follow-up to mean value theorem once we add that extra condition. But the reality of mathematics is that it actually started with Rolle's theorem, and Rolle's theorem is actually necessary as a proof, as the part to prove mean value theorem. So that's why we continue to present them as two separate theorems. Okay, but now, as we finish this video, let's just do one problem. Let's start off with a given function, f of x. This problem we're going to do as a graph. I'll mention a quick one with respect to an equation, but it's really the same idea. So let me start this off. This is given to you. You're given this function f of x. And our graph does this. And initially, oh, so that's given, and I'm sorry, let me finish the graph. So that does that, and that does that. So that is our whole function f of x. And here's the question. We'll do 4 questions here. Does Rolle's theorem apply to f of x on the interval 1 to 3? Our second question, if yes, find the C guaranteed by the theorem. And then we'll do 2 quick follow-up questions with mean value theorem. Does mean value theorem apply to our function f of x, but this time we'll change our interval and we'll go from -2 to 1. And then similarly, if yes, find the C. If you start looking ahead in your homework, there are some problems exactly like this. We can talk about the idea of, again, using the graph and just checking these conditions with the graph. If we have the equation, it's the same idea. How do you know about continuity? You look at the equation and you think about discontinuities. How do you know about differentiability? Well, you look at the derivative and think about problems about x values where the graph is not differentiable. So it's not that bad. It's almost the same thing that we have with this graph. So now going back to the top, does Rolle's theorem apply? Well, we've got the 3 conditions to check. Is f continuous from 1 to 3? And the answer is yes. Here to here, all of this is connected. Yes. And especially with the graph, there's nothing else to say. That's all there is. We look at it and we see that it is. Similar with the next one. Is f differentiable from 1 to 3? And the answer, once again, is yes. Now, I don't know if you could tell, I was trying to make a sharp point right at 1. But that's still not an issue here, because it's all about the inside. So even when we do the next part, when we go from -2 to 1, same thing. All of this is fine. This would be the tough spot, but right at 1, we're not concerned with. So same thing. No sharp points between these two, so that is also true. What about f of 1? Does that equal f of 3? In an equation, we'd have to plug these x values in to see the y's, but with the graph, we just look. F of 1 is 2, f of 3 is 2, so that is also a yes. We said yes to all three conditions. So yes, Rolle's theorem does apply to this function. Well, so yes it did. Now let's find the c. The c is the value that has the horizontal tangent line, where the slope is 0. And that would be right here. All right, just looking, there's only one c value here. C would equal 2. 2 is a value between 1 and 3, such that the derivative at 2 equals 0. Okay, and now we'll very similarly do that with mean value theorem. Does mean value theorem apply on this interval? Well, now only the two conditions. Is this function continuous from here to here? Yes, it is. No breaks or holes. Is this function differentiable between here and here? Yes, it is. Between here and here, no sharp points. So, yes, mean value theorem does apply to this function on this interval. But now, what about the c value here? It's a little bit tougher here, but because we just need to visualize a little more. It's a little easier to think about a horizontal tangent line. In this one, if we're going to think about what this tangent line should look like, it'll really help if we draw the secant line. Draw the line that connects the point at -2 to the point at +1. So roughly, that would be my secant line. Remember, I'm just doing this as a rough sketch. And now, same thing, I'm going to ballpark my c values. If I think about drawing tangent lines in between here, can we see a spot where the tangent line is parallel, has the same slope as this secant line? I would say one of those values is about right. Maybe it's about right here, actually. So maybe not right at -1, so maybe just in front of it. So maybe c equals about 0.9. I would not give you a hard time at all if you said it was -1. I'm sorry, -0.9 here. I would not give you a hard time at all if you said that happened at -1. But it does look like it's just a little bit past here. And there's actually a second one. This is kind of like what we were seeing with the examples earlier. We found a c value, and that is a perfectly good answer, but realized someone might have focused on this value and said there's their answer, but someone else might be up here. Roughly about this point also has a tangent line that is parallel to this line. So you might also say, see, it's not quite 0. Maybe that's about -0.1. So two possibilities for that one. And like I was saying before, I'm not going to go any further with that. There are a few good problems, and I'm happy if you ask a few questions and people want to see a little bit more. But again, this is a nice quick section, introduce some nice important theorems, but for our purposes, we really need to get into the extremes and the critical values from 3.1. And our next video, as we get into 3.3, we'll get more into the local extremes and start talking about more properties of the first and second derivative.